This is the third video of Module 3, and which is actually a segue to what we're going to spend time on in Module 4 mostly. Starting with a quick survey of organic functional groups. So you can break these down into structural classes, keeping with what we've learned so far. For example, sp3 hybridized functional groups. Remember, these are tetrahedral in geometry. So you have an alcohol group. And remember, there are two lone pairs there that are implied. So you don't always have to draw them in, but I would recommend drawing them in the first 25 times until you won't need to know that you won't need to draw them in anymore. You'll know that they're there in your head, just like all the other implied atoms. This is an ether. So an oxygen bound to two other carbons. And I've just drawn really simple structures here as general structures. There could be all kinds of other things attached on both sides. But an ether is an oxygen bound to carbons on both sides. So if it's not carbons on both sides, it's not an ether. What we're trying to do here is just for this part of the module, be able to recognize and name the functional groups if they're present in molecules. This is an amine, and the nitrogen has a has a lone pair to have no charge. Remember the octet rule and formal charges. This is a thiol. Sulfur is right below oxygen in the periodic table, so it's going to have basically the same bonding, although sulfur can have more than an octet. It doesn't often. Maybe I shouldn't say that. It does, but not as often as you think. So another sulfur-containing functional group is a sulfide. And notice how this is really similar bonding to oxygen in water, or the oxygen above in the ether. So a thiol is similar to an alcohol. A sulfide is similar to an ether. So those are all the sp3 hybridized functional groups for now, I'll say. There's sp2 hybridized functional groups. They're trigonal planar. We already know the alkene. That's a functional group. Alkenes are reactive. This is a ketone. And again, it's implied here that there are carbons on both sides. This is an aldehyde. You need to be able to recognize the functional groups, name them, and spell them. So an aldehyde also needs a carbon group on one side of it, but there could be all kinds of other stuff extending onward. This one is an ester. Not to be confused with ether. They're really not similar, but somehow people get those confused. Ester and ether, pretty different. Esters are connected to a carbon group there and another carbon group there. This is a carboxylic acid. Connected to a carbon group there, and it has this arrangement. This is an amide. Not really supposed to be called amide. Some people call them amide. It should be amide. Connected to carbons on both sides usually. However, this could be a hydrogen on this side, and it would still be called an amide. This is a benzene ring. Probably you recognize this already anyway. In Organic 3, we spend a ton of time on the chemistry of benzene rings. But we see them a lot anyway, and they're a functional group, essentially. Sometimes referred to as aromatic rings. But there are other aromatic rings besides benzene rings. sp hybridized functional groups, linear. We've already seen alkynes. So you're not going to have to memorize some of these because you already know them. This is a good one though, a nitrile. A nitrile group. And I've thrown in the carbon just for clarity, but if you look at the alkyne, that's what that looks like if you draw in the carbons on both sides of the triple bond. The concept of a functional group is important to understand. So here's an analogy, maybe not the best analogy, but you know, a leaf is a leaf. A branch is a branch. When you see something like this, do you call it a leaf branch? No, you call it a tree. So the word tree has a meaning that conveys all of it, not just a part of it. And for want of a better analogy, if we look at the carboxylic acid, this is not a ketone and an alcohol. You would never refer to this as an alcohol or this as a ketone. You would refer to all of it as a carboxylic acid because they're together. So no on those, you know. So another example, here's a ketone, here's an ester, as we saw above. This is a functional group. If you put the two together, basically, well, sort of. It's not a ketone plus an ester. It's not a ketone ester. It's not a keto ester. It's an anhydride. So there are a lot more functional groups than what I've shown you, including anhydrides, lots and lots of other specialized functional groups. So the other part of a concept of functional groups is that they impart the function to organic molecules. So you can think of the carbon framework as the skeleton and the functional groups as the active portions. The activity of functional groups revolves almost entirely around electron movement and electronegativity, which also relates to concepts like inductive effects and polarity. Those are good words to look up. But we're going to get into those a lot more in Module 4. Wouldn't hurt to look them up now. The movement of electrons, which is used to predict reactivity and activity, is developed into what we call a formalized system or formalism of arrows, symbols as arrows. So when you have electrons moving, say a lone pair of electrons, we indicate the movement of two electrons by just a simple curved arrow. Movement of two electrons. As an aside, the movement of one electron, which can happen also, we're not going to cover this right now, is a half arrow. So that's part of the formalized system as well. Electrons caught up in bonds can react and move as well, and we note that with a curved arrow as well. So on the left you have a bond forming arrow, and on the right you have a bond breaking arrow. Formal charges are critical in understanding activity and reactivity. So here we have an alcohol group and a hydroxide ion. If we did not have this negative formal charge, we would be hard-pressed to maybe predict the reactivity of this reaction. Because this is negatively charged, we can indicate a 2-electron bond-forming arrow to the proton, which, remember, is a proton in the nucleus, and its electron is bound up in this bonded pair. So protons are positive, and we have negative to positive bond forming. because hydrogen can't form more than one bond at a time, it pushes these electrons out toward the more electronegative oxygen, which makes sense, right? Because oxygen is electronegative and electrons would want to go toward it. So this is bond breaking because hydrogen can't form more than one bond. The result of those arrows is that you now have a new lone pair from the broken bond and a negative formal charge, and a new bond that's formed from the oxygen to the hydrogen here. I could have indicated the other one. And no formal charge. So you need to quickly reassess formal charges throughout reactions. And you see why formal charge is so critical to understanding. Below I have the same reaction drawn out like you would have seen it in general chemistry. And I can't overstate this, which is why I wrote science up here, because notice this is science because it helps us predict reactions, perhaps reactions we haven't seen before. It's an understanding what is going on. I call this magic because there is no way to understand what's going on in this reaction in general chemistry. Yes, you can use this kind of notation to balance reactions, but frankly, who the hell cares? This is a small skill, really, relegated to selected research groups that might need to balance reactions like this for some other purpose, but largely organic chemists are thinking and working in terms of the top because it indicates understanding of what's going on, not just some kind of magic swapping of atoms. If you look at this reaction, all you can tell is that one of the hydrogens has magically appeared over here. It's magically switched places, but you have no idea why. So that's my rant for the day against general chemistry methods. I can go on and on. Here's another reaction, just like the one above. It looks a lot different, right? But if you look closely, it's not. It's just that all of this is different. But the components of the functional groups are identical. You can draw your arrow like this, and I should have drawn a bond in here. I could draw my second arrow in there carefully. Those are the same two arrows that you see above. The outcome is identical. And notice you didn't have to memorize a new reaction, because it's really the same reaction as what you see above. It really is. So in learning and understanding one reaction, you can understand a million reactions, because anything could be attached here. And it's the same reaction. All of the action takes place at the functional groups. Same point made here. How on earth would you know what C5H10O would do with OH minus without understanding the structure, bonding, and reactivity, and using the arrow formalism? You just simply can't. We might now even be able to understand what's going on here, or predict. Let's say we have an amine reacting with an acid. Well, these electrons are reactive as a lone pair, and if they can bond here in a bond-forming reaction, movement of electrons, not movement of atoms, and then the hydrogen, for the same reason above, cannot form two bonds, so these electrons will go toward a plus charged oxygen. So you could look at this part and say, this bond right here is breakable because it can go toward a plus charged oxygen. So that means this proton, messing it up a little bit, can be removed by a pair of electrons that can form a new bond to it. Our predicted and correct structure of the product would be this. It generates neutral water with 2 lone pairs. This had a lone pair here, by the way. And nitrogen, though, now you have to reassess formal charges. That's a plus charge nitrogen. Same point made again. How on earth would you know that C5H11N and hydronium ion would form what product it would form? You wouldn't. You can't. Unless you understand what's going on. So we're going to spend a lot more time on this. I think the key points probably been hammered home well enough. You want to be able to recognize functional groups within a structure like you see on homework 3. And just basically recognition at this point, but soon we're going to go into a lot more understanding of chemical reactivity.